Much of the philosophical conversation in this series so far has centered on metaphysics, the study of reality. What exists? What is the universe made of? A distinct, although related field in philosophy is epistemology. Epistemology is the study of knowledge. The classical definition of knowledge is true justified belief. Just because you believe something doesn't mean you know it. You may believe that I have a sister, but because I don't actually have a sister, you can't know that I do, no matter how strongly you believe it. For a belief to be knowledge, the belief must be true. But truth is not enough. You have to have a true belief for the right reason. Let's say that you believe that I have a scar on my left side, just below my armpit. And let's say I do have a scar there. You would have had a true belief about me. Did your true belief mean that you knew about my scar? It depends. If we asked you why you believe that I have a scar in this particular location, you may say, well, I know Steve appears to be human, but I believe he's really from the planet Arbulgar, and all beings from Arbulgar have a third arm on the left side. If he was going to pass himself off as human, Steve would have had surgery to remove the third arm, and that would have left a scar. That's why you believe there's a scar there. Truth is, I am human. I was born on Earth to Earthling parents, but when I was 13, I ran into a building to save a dozen orphans and their pet puppies and kittens. All got out safely, but in the process, I suffered an injury to my left side that left a scar. You believe something that accidentally turned out to be true. You believe a true proposition, but believe it for the wrong reason. Knowledge requires that you hold not only a true belief, but a justified true belief. That is, a belief that is true for the right reason. The obvious question is, what counts as the right kind of reason? With respect to scientific theories, our interest in this course, the epistemological question, is what gives us grounds to believe that a given scientific theory is true? What are the marks of a successful scientific theory? One virtue that should be considered to convey such a warrant for reasonable belief was proposed by the 19th century scientist and philosopher William Whewell. Whewell was responsible for adding science to the graduation requirements at Oxford, thereby making knowledge of science a general expectation for an educated person. He was a wordsmith who created terms like ion, cathode, anode, electrode, linguistics, and most importantly, he's the person who came up with the words physicist and scientist. He was a scholar of the history of science, noting that the most successful theories in all of the history of science shared a common property, unifying our picture of the universe. Successful theories were not only able to account for the phenomena they were designed to explain, but could also be used to explain seemingly other areas of study. The term he created for the property of unexpected expansion of the realm of explanation is consilience. A theory is consilient if it's able to account for what had previously been considered disparate areas of science. In bringing them together under a single explanatory theory, they're seen as being a part of the same thing. Consilient theories unify our picture of the world, and this is a mark of truth, Whewell contended. A second, seemingly similar virtue for acceptable theories was provided by the 20th century philosopher Karl Popper. Popper contended that better theories are bolder theories. We ought to reward theories that are the riskiest, the most general, the broadest in scope. Popper's virtue of boldness emerges from his interest in what we call the problem of demarcation. This is the question of drawing the line between that which is scientific and that which is not. Popper began writing in Austria in the 1930s and 40s when there was a sudden deep cultural interest in topics like ESP, seances, and Nazi race theory, all of which claimed to be scientific. Popper saw that the rise of pseudoscientific belief, or rejection of belief in legitimate science, in a culture could set the stage for horrible things. And so he sought to clarify the epistemological line that divides that which is truly scientific from that which is not. What we believe in part determines how we act. Science helps us determine what's rational to believe and therefore helps us determine what is rational to do. If we can't separate the real science from the fake science, we could end up doing horrible things to each other and to the planet. So, we need to determine the feature or features that define what it is to be scientific. Popper thought that the goal of science is to account for the behavior of the universe. So, the minimum that we should expect from any proposition that claims to be scientific is that it says something about the universe. A sentence has to have empirical content to count as scientific. But how do we determine which sentences have empirical content? The logical positivists, like Rudolf Carnap, whom we've mentioned multiple times in this course, argued that we needed a criterion of cognitive significance to do this job. They thought that a sentence would be meaningful if and only if there's evidence in support of it. If you can tell me what I would need to see, feel, taste, hear, or touch to have good reason to believe the sentence is true, then it's scientific. For this, we needed a complete account of scientific evidence. And this was a project that wasn't going particularly well for the logical positivists. Popper, who was also from Vienna but never received an invitation to join the circle of logical positivists, and forever had a chip on his shoulder about it, took the question in completely the opposite direction. He realized that saying something about the world is taking a risk. You risk being wrong. The key is not to focus on positive evidence, that which supports you, but rather on negative evidence, that is, on the possibility that you might be wrong. Any sentence that has empirical content, that says something about how the world is, could be false. Maybe it is, maybe it isn't, but it's possible for it to be. If you're telling me something meaningful about how the world is, it means the world could have been otherwise. There's a set of possible observations that, if observed, would prove you wrong. Popper called this property falsifiability. A proposition or a theory is only scientific if it's falsifiable. We have to be careful, though, to distinguish between three different notions here: false, falsified, and falsifiable. So, a sentence is false if what it says about the world is not how the world is. So, the sentence, "Steve is wearing a plaid tie," is false because the tie I'm wearing is not plaid. False means that what the sentence or theory says about the world is not the case in the world. A sentence is falsified if it's shown to be false. Your observation of the pattern on my tie falsifies the claim that Steve's tie is plaid. Observations that show the sentence to be false are falsifiers. A sentence or theory is falsifiable if and only if there are potential falsifiers. It doesn't mean the sentence is false, just that it could be if the world were a certain way. Consider the sentence, "Steve has a beard." This sentence is not false. I do have a beard. But even though it's not false, it is falsifiable. That is, there are potential falsifiers. If you looked at the screen and you saw me clean shaven, that would have falsified the claim. To be falsifiable does not mean it's false, but that the world could be a way that would make it so. If that's possible, then the statement or theory says something meaningful about the world. To count as scientific, a theory has to be falsifiable. That is, it has to be possible for it to be wrong. Some theories lack this. Consider what we call psychological egoism. This is the view that humans can only act in their own self-interest. If I give you examples of people acting selflessly, the egoist would respond, "Well, but they're doing it because it makes them feel good. See, it really is for them." If I then cite cases where the person grudgingly does something for someone else, the egoist might make the move, but subconsciously they're gaining pleasure. They just don't realize it. What this move does is eliminate all potential falsifiers. The theory can't be false, so its truth means nothing. It doesn't actually describe anything. To be scientific is to have some chance of being wrong. Science requires risk. The best scientific theory, Popper argues, is the riskiest, the boldest scientific theory. That is, the best scientific theory possesses the most potential falsifier. The greatest teams in sports history would be the teams that played the most games against the most talented opponents. Each game is a chance for the team to be defeated, yet the team prevailed. In the same way, the more the theory could be wrong about, but isn't, the better the scientific theory. Maximal falsifiability is maximal riskiness, and that is what we should celebrate in science. Whewell and Popper's virtues could be perfectly consistent. In fact, most times, consilience increases falsifiability. If you come up with a theory for A, and it can be understood to also cover B, then all of the predictions it makes about B are now potential falsifiers. You've doubled the falsifiability of the theory by being consilient. Both Whewell and Popper would applaud your theory. But this is not always the case. Sometimes you can have one virtue, consilience, without having the other, falsifiability. What then? Do we really need to worry about it? This isn't the usual case in the history of physics, right? Take Isaac Newton. Before Newton, we had the Aristotelian view of the world, in which terrestrial physics and astronomy were distinct sciences governed by completely different principles. But then, Newton's mechanics and law of universal gravitation united them into a single study. It unified falling apples and orbiting planets. Consilience with an increase in falsifiability. James Clerk Maxwell brought together bits and pieces of work on electricity and magnetism into a single coherent theory of electromagnetism. And out popped an account of optics, the physics of light. Unbelievable consilience and a major increase in falsifiability. Einstein's theory of special relativity brought together mechanics with Maxwell's electrodynamics. His theory of general relativity then also included gravitation. Both steps, consilience with an increase in falsifiability. The process of physics up through the middle of the 20th century was a story of increasing unification. And then came quantum mechanics. In the middle of the 20th century, physics had two theories, general relativity and quantum mechanics. Both were tremendously falsifiable, but had not been falsified. Each made slews of predictions about the world and, every time, got it right. We had a pair of incredibly successful theories. One about things that are big and one about things that are small. We just needed to bring them together into a single picture of the universe, and we'd have the whole problem of the universe solved. Physics would be done. Famous last words. In 1935, Albert Einstein, along with Boris Podolsky and Nathan Rosen, proposed a thought experiment that illustrated the trouble that would keep quantum mechanics and general relativity from being easily assimilated. We say that an electron has a property we call spin because mathematically it behaves like rotation. Right? We can create pairs of electrons that are what we call spin correlated. That is, in order to obey a conservation law, the electrons will have opposite spins. If electron A has what we call spin up, then electron B will have spin down, or vice versa. But recall from quantum mechanics that when we did not observe a system, it would be in a state of superposition. That is, it'd be in a combination of every possible state it could be in. The Schrödinger equation gives us this mathematical combination that describes how things are, and this holds until a measurement is taken. So, if we create these spin-correlated electrons, but don't look at either one, then both are in superposed states of up and down. But the instant we look at one, it goes from the superposed state into a single value of the property. Since the two electrons are spin correlated, by observing electron 1 and finding it to be, say, spin up, then electron 2, in order to obey the conservation law, must acquire the spin value down. So we have two electrons in superposed states, and because they're correlated, observing one causes both to instantaneously and simultaneously collapse into a single but opposite property state. But now, Suppose we created the particles at a facility at the University of Kansas, right in the middle of the United States, and then sent the electrons east and west, one to Columbia University in New York and the other to Stanford in California, but we measured neither. So we have electron A on the east coast in a superposed state and electron B on the west coast in a superposed state. But at Columbia, somebody gets impatient and checks the spin. You know how those New Yorkers are. Because the measurement was taken, electron 1 now acquires a single spin value, let's say up. But that means that at that very instant, electron 2 in California had to go from a state of superposition to the single value state spin down. The question is, how did electron 2 know that electron 1 was measured? The only way it could know is if a signal was sent. But to get it across the width of the United States, that signal would take time. But no matter the time, we could have measured the Stanford electron after the Columbia measurement, but before the arrival of the signal from Columbia, and always have gotten the result spin down. Making that time gap small enough forces the signal from electron 1 to electron 2 to move faster than the speed of light. But according to the theory of relativity, no signal can move faster than the speed of light. But quantum mechanics says that it would have to in cases like this. Physicists refer to this as spooky action at a distance. And it's ruled out by relativity, but required by quantum mechanics. The two theories seem to be incompatible, inconsistent, contradictory. Can you unify theories that contradict each other? Einstein, of course, thought you couldn't and would have to replace one of them, quantum mechanics, with a better theory. The better theory came, but it didn't replace quantum mechanics. It only extended it. There are four seemingly distinct forces in the universe known to us. The two we've known about the longest are gravity and electromagnetism. To explain how electricity and magnetism work, Maxwell and his teacher Michael Faraday developed the notion of a field. A field is a space with a little arrow attached to each point of the space. The arrow at each point will change their size and direction, but do so in concert with the arrows and the points around them so the changes are smooth. Einstein used this idea as well when accounting for gravitation. Indeed, the equations of the theory of general relativity are called the Einstein field equations. The theory of gravitation is about the behavior of the gravitational field. So, it seemed to many, including Einstein, that we ought to be able to take these two field theories and bring them together into a theory about one field that accounts for both the electromagnetic and gravitational forces. This would be a unified field theory. Indeed, this was the project that would occupy Einstein until his death. Theodore Kaluza and Oscar Klein independently worked on such a theory, what we call the Kaluza-Klein model, that for a while showed great promise. They were able to add relativistic gravitation to Maxwell's electromagnetism through a trick. The trick was to add an extra dimension to space. Now, the space we see has three dimensions. It's possible at any point in space to draw three mutually perpendicular lines. There doesn't seem to be any other way to add another one. But Kaluza and Klein found a clever way to do it. Roll up the extra hidden dimension. At each point in space, attach a little ball, like a pom-pom to a knitted winter hat. We could now have the arrow of the field point move around the ball in ways that contains the extra information needed for the theory to account for both gravity and electromagnetism. Now, for technical reasons, the theory didn't work, but the idea of adding extra dimensions and rolling them up at points, that's one we're going to see again. Einstein approved this project of finding a unified field theory for the two original forces of gravity and electromagnetism, but it was eclipsed by the progress of physics when we started to look more deeply at atoms. J.J. Thomson discovered the electron. Atoms were not the uncuttable bits that the classical Greeks considered, but rather had parts, one of which was negatively charged. He embedded these negatively charged nuggets in a goo of positivity in his plum pudding model of the atom. The model was rejected when Ernest Rutherford discovered the nucleus. The positivity was jammed into a tiny hard kernel. This gave us the solar system model of the universe, with the nucleus playing the part of the sun and the electrons revolving around its planets. Now, there are three problems with this model. First, if the nucleus was made up of positively charged particles, protons, jammed together very tightly, the electromagnetic charge would blow them up. Positive and positive repel, and they repel harder the closer they are. So there would be no way the nucleus could hold itself together. If we're thinking of things clinging together, the obvious answer is gravity. But gravitation is far too weak to do the job. There would have to be another force, a third force in the universe to account for it. This force would have to be very strong, but active only over very short distances. It's only observed at work in the nucleus of atoms, and so became known as the strong nuclear force. We now have three forces that need to be accounted for in nature. The second problem for the solar system model of the atom is radioactivity. Every once in a while, at predictable rates, a particle will get shot out of the nucleus with high energy. Why? How? We have three forces: gravity, and the strong nuclear force that hold things together, and we have the electromagnetic force, which can be repulsive, but is overmatched already by the strong nuclear force. What's the gunpowder that shoots out the particle in a radioactive atom? It had to be another force. We called it the weak nuclear force. Now we had four forces. The third problem for the solar system model was one we discussed a few lectures back. Right? The first two problems were problems of the nucleus. The third is a problem for the electrons. Moving electrical charges create magnetic fields, and this requires energy. So if the electrons are going around the nucleus, they would be losing energy and thereby spiraling into the nucleus. Atoms should be collapsing. They shouldn't be stable, but they are. The answer to this came from Niels Bohr, and that answer launched quantum mechanics. So, the emergence of the two new forces were entangled through the investigation of the atom with quantum theory. The result of this is that when electromagnetism was brought into unification, it was not, as Einstein hoped, a unified field theory of electromagnetism and gravity that emerged. Rather, it was a unification of the new nuclear forces and electromagnetism in the advanced quantum theory. Einstein had thought he could marry gravitation to electromagnetism, but the new quantized nuclear forces stole his fiancée. The first unification was the electromagnetic force with the weak nuclear force. This gave us quantum electrodynamics. Next, the strong force was unified with the others, showing that three of the four different forces we observe in nature are just different aspects of a single force. This gave us quantum field theory. These were unifications that would have pleased both Whewell and Popper. At each step, we not only achieved the sort of conceptual coherence that Whewell described with his notion of consilience, but doing so predicted the existence of new particles and new phenomena that could be observed. When we looked at the results of carefully executed experiments with high energy particles and particle accelerators, we found almost everything we hoped to find. Quantum field theory was bold, made risky predictions that required empirical data. Popper, like Whewell, would approve. So, this left us with two distinct field theories. General relativity, that gives a description of the gravitational field, and quantum field theory, that gives us a description of the field that accounts for the other three forces, electromagnetism and the weak and strong nuclear forces. And that's where we stand. Indeed, that's where we've stood for decades. Two field theories, both right about everything they predict, but seemingly incompatible. They can't both be right, but neither is wrong. Quantum field theory has been used to develop the Standard Model, which categorizes every particle and force in the universe. Since we have the duality of energy and particles, even the four forces can be thought of as particles that get exchanged when a system experiences an interaction involving that force. So, The Standard Model divides the basic stuff of the universe into two large categories according to the sort of mathematical statistics that govern their behavior. Those that are governed by Fermi-Dirac statistics are called fermions, and are what we usually think of as the stuff, whereas those that obey Bose-Einstein statistics are called bosons and are what we usually think of as forces. Fermions come in two flavors. One flavor is the set of quarks, and these come in three pairs: up, down, top, bottom, and strange charmed. These make up the protons and neutrons. The other flavor is a set of leptons. These also come in three pairs: electron, electron neutrino, muon, muon neutrino, and tau, tau neutrino. Bosons also come in two flavors. Gauge bosons are the virtual particles related to the four forces, and the lone scalar boson is the Higgs boson, which is responsible for giving particles their mass. We have this wonderful map that plots out everything neatly and seemingly completely, with the exception of gravity, of course, but which lacks an underlying account of how it works. Enter string theory. First proposed in the 1980s, but developed through the last couple of decades, string theory provides us with a possible picture of what's giving rise to the Standard Model. Making use of a picture somewhat similar to what we saw decades earlier with Kaluza-Klein, we think of something attached to each point of the field, but instead of a little pom-pom, it's a little string. Now, strings can be open, stretched out like a line and vibrating in a number of ways, or strings can be closed, that is, a loop, which also can vibrate in a number of ways. The modes of the open vibrations are correlated with the different fermions. The different modes of closed loop vibrations are correlated with the different bosons. String theory has the great virtue of giving us an image that explains everything in the Standard Model, but it also appears to have the greater virtue of being able to do it in a way that accounts for the general theory of relativity. If we take the universe to be the way string theorists claim, then we may well be on the path to a complete, unified field theory of everything. This, its supporters argue, demonstrates its likely truth. The epistemological argument they make is one right out of Whewell. What we get from string theory is consilience of the highest conceivable order. We have a single theory that would, if true, unify our best theories covering the entire range of phenomena. Unification is a sign of truth, and string theory is the ultimate unifier. Therefore, string theory is probably the ultimate truth. But there are opponents of the theory, and they point out that while it's true that we have Whewellian consilience with string theory, what's lacking in the theory is Popper's falsifiability. The usual case of consilience, when a single theory gets applied to multiple fields, results in increased falsifiers. If my theory that's intended to explain all the phenomena in field A is suddenly applicable to field B, it now makes predictions in both A and B and therefore has twice the possible falsifiers. Extension like this makes a theory bolder, riskier, and therefore better. But in the case of unification here, we already have a theory that covers all of A and a theory that covers all of B. String theory gives us a nice heuristic picture to hold in our heads. But what it does not do is go beyond these two to make new predictions. There's consilience without an increase in falsifiability. There's a peeling away of the Popperian virtue from the Whewellian virtue. And the point of Popper's falsificationism is that the degree of falsifiability corresponds to the empirical content of the theory. If the theory is not falsifiable, then it says nothing about the world. If it says nothing about the world, then it's not science. This is why opponent Peter Woit says that string theory is not even wrong. To be wrong is to make a claim about the world and have the world not be that way. If you said, I have a sister, you'd be wrong because you made a claim about how the world is, but it isn't that way. But with string theory, because it only accounts for that which is already accounted for without adding any new empirical content. That is, because there are no new testable consequences. The theory is vacuous. The theory is not right because it can't be wrong. Is string theory right? Is it wrong? Could it be wrong? The question is both physical and philosophical. And what's interesting is that the cutting edge of contemporary physics has the physicists themselves being philosophers. We started this series asking how one could see physics and philosophy as related. Physics started as a branch of philosophy, but then veered away. It turns out that at its cutting edge, the two have come back together.